We want to build a kernel and a root file system for a QEMU emulated board where to run interesting binaries of our IoT device, but our device has a very old kernel, libraries and packages. This means that we need to run an old Buildroot version or other old tools that will not run on our current Linux desktop, but they will run on old Linux distributions. To overcome this problem in a simple and fast way, without the burden and overhead of a virtualization environment, we will introduce Docker, which can be configured to run older tools transparently on our modern Linux distribution. I am Valerio Di Giampietro. I am an electronic engineer with a background in digital electronics and information technology infrastructures. I would like to be your friendly Italian hacker neighbor willing to share with you tools and techniques for hardware hacking that I learned by myself hacking many devices. If you have not done yet, please subscribe and click the notification bell below to be notified when new episodes will be released. And now, let's start! This is the 8th episode of the series Hardware Hacking Tutorial. In this complete series, we'll talk about the hacking process based on information gathering from our device, building an emulation environment where to run interesting binaries, discovering how the device works, and then hack the device and modify its firmware. This episode is about how to use Docker to build the emulation environment using all the tools, like all the versions of Buildroot that don't run on modern Linux distributions. We have to use a container environment like Docker or a more complex virtualization environment to solve this issue. This argument is not strictly related to hacking, but it is a very important tool needed to move forward with the Buildroot installation, configuration and generation of the kernel and the root file system for our QEMU-based board emulation environment. Docker is a very useful tool that can be used in many different situations. It is a light and efficient tool to package everything is needed to run complex tools in a well-defined environment. We can include an entire Linux distribution in a Docker image. It can be particularly useful in the embedded space where often there is the need to rebuild some software on devices that are on the field for many years and a very old toolchain is required. It is an easy-to-use tool, but it is important to know some basic concepts that we will explore today. In this episode, we will use as an example the same sample Gemtech router we used in the previous episodes. We want to build a kernel and a root file system that is reasonably similar to that of our device. This usually means that we want the same kernel version as in our IoT device with similar configuration, same preemption model, same named drivers, same file system support, etc. We could also use a different kernel version, but it would be better to stick with the same version. In our sample router, we have kernel version 2.6.36 that was released in 2010. We want also the same libc implementation and version. This is more important than the kernel version because if it's not the same, there is a high probability that the device executable binaries will not run on the emulated environment. This happens because in the embedded devices it is common to use specialized libc implementations to save memory, disk and processing power. These implementations often are not fully compatible with one another or with different versions of the same implementation. Some of the more popular specialized libc implementation are musylibc, musylibc-ng, musl, dietlibc and some others. In our sample router, we have musylibc version 0.9.33.2 that was released in 2012. We need also the same or compatible versions of libraries used in the executable binaries we are interested in. In our case, we have libssl 1.0.0, part of the OpenSSL package that was released in 2010. As we have seen in the previous episode, our sample router, manufactured in 2017 and distributed for a couple of years, has very old software. Unfortunately, this is quite common on embedded devices. This means that we have to build a root file system with very old software. We cannot use the latest Buildroot version to build the kernel and the root file system because the latest version has moved forward with kernel libraries and package versions. We have to use an older Buildroot version that, as much as possible, has the components we need, especially the specialized libc implementation. Maybe we have to download a lot of different Buildroot versions to find the one we are interested in, and when we have found it, usually all other library versions are more or less of the same age as the libc, and usually are the same version or similar version as in our device, where every component have more or less the same age. In our sample Gemtech router, it is much easier to find the correct Buildroot version because the router itself has been built with Buildroot, and its HOS release file tells us that it has been built using Buildroot version 2015.02 SVN 12502, so probably they have used version 2015.02 imported in their subversion repository, made some little modification and internally released as this version. By the way, Subversion is a source version control system as it is Git. It was very popular before Git and it is usually abbreviated with SVN. This means that we have to use Buildroot version 2015.02 released in February 2015. One of the problems of older and complex software as Buildroot is that it will not run out of the box on a recent Linux distribution. Buildroot first of all recompiled the entire toolchain needed to do cross-compilation for our device architecture. This means recompiling GCC and all of the GNU binutils. Then it uses this toolchain to build the kernel and the other libraries and packages for our target device. It is very easy that slightly different GCC versions or glibc and other library files can give errors that were not present in older Linux distributions, and trying to fix all of these errors can be time-consuming and can be like a never-ending steeplechase. The easiest fix to this issue is using an older Linux distribution, and distribution that has more or less the same age as the Buildroot version we are trying to use. We could use a virtual machine, but we will use Docker that gives us a better result. It is faster, it uses much less resources, and it is easier to share files between the Docker machine and our host environment. In our case, I wasn't able to successfully run Buildroot version 2015.02 on my Ubuntu 18.04 and my Ubuntu 19.10. I was successfully on Debian Wheezy released in 2013. Docker is very popular for building the modern IT infrastructure based on microservices running on a scalable architecture with many independent Docker machines that are called containers. It is a much more accurate definition than machine. We will use Docker differently as a sort of very efficient virtualization layer to run all the software on old Linux distributions inside our modern Linux host machine. In our case, we will not use so much the isolation feature between the Docker container and the host machine that instead is usually at the core of Docker infrastructure deployments. It is very easy to install Docker on our Linux PC, as we will see soon. After installation, the user running Buildroot must be a member of the Docker Linux group to be able to launch Docker. Docker is a very nice and well-architected packaging of existing Linux technologies. At its core, it uses the chroot environment. In this way, a process started on chrooted directory will search all of its files, like library files, configuration files, and so on, starting not at the real root of the file system, but at the specified new root. This means that, for example, if in this new root we will put under the directories h, var, lib, bin, and so on, the directories of another Linux distribution, this process will use that files as if it was running on another Linux distribution. In reality, it is a process running on our host machine, on the same host machine kernel. It is only using different library files and other configuration or executable files. Another core Linux feature used by Docker is the so-called namespace isolation, a similar concept to that of a local variable in a function. This is a Linux feature to have a process with limited visibility of the namespace of the entire system. This means that, for example, if this process uses standard Linux library calls to have a list of processes running on the system, it will see only itself and eventually other processes that it has created. If it asks for a list of available Ethernet interfaces, it will see only what has been configured to see, and so on. It is a situation similar to that of a process running on a virtual machine that can see only what is available on the virtual machine and doesn't know the resources available in the host machine. The third important Linux feature used by Docker is the so-called cgroups. That is the possibility to group processes and assign to these groups the maximum amount of resources that they can use. For example, we can assign to a group of processes the maximum amount of RAM they can use, or the maximum percentage of CPU, or the maximum disk bandwidth, and so on. Using cgroups, it is possible to limit the maximum amount of resources a Docker container can use. This means that using the chroot environment, the namespace isolation, and the cgroups to limit resource usage, a Docker container will be similar to a Linux virtual machine, but it will run on our sample kernel. It will be a process or a process tree inside our host machine, and it will start in few milliseconds. A virtual machine, instead, usually needs at least few seconds to start and has the overhead of an entirely different kernel running. Another nice feature of Docker is that we can start a container using a simple configuration file. It will do its job, and when we terminate it, all modifications done inside the container disk is lost. When we restart this container, it will be as if it has just been rebuilt from scratch. In this way, we are always sure that the just started container has everything it has to have without some unwanted packages or library upgrades done by a previous system administrator. If we want to have a permanent storage, we can easily mount host directories inside the Docker container, and only these directories will keep the modifications done by the Docker container after the container is terminated. There are other ways to have permanent storage inside the Docker container, but the core concept is the same. A Docker container is created using a Docker file that is an amazing simple file to describe a machine. The Docker file for our Debian Wheezy Linux is shown on the screen. The first line tells that we are starting from a minimal Debian Wheezy official Docker distribution that will be downloaded from the official Docker Hub repository. In the end-of-line section, because it is all the Linux distribution is end-of-line, that means without more updates and support. The Docker Hub is a repository where we can find thousands of ready-made containers from almost every Linux distribution to special-purpose containers already configured and ready to run. You will find the link in the description below. An interesting feature of Docker and its Dockerfile is that it has a layered file system, so it will download from the Docker Hub repository the layer for Debian Wheezy, and for each line of the Docker file it will add another layer on top. This means that if we change something in the Docker file only from that line onward, the various layers will be rebuilt. This means that once downloaded the Debian Wheezy image, it will not be downloaded anymore. If some other Docker file in our Linux machine will use the same Debian Wheezy image, it will use the same file system layer without another download. The second line specifies the Dockerfile maintainer. The line 6 is a definition of an environment variable. In this case, I used a variable name and this value to define the version of this Dockerfile. The interesting thing is that because of the layered structure of the file system, if I want to force a rebuild of all layers after this line, I can change the line, incrementing, for example, the version number. The lines 12 and 13 defines environment variables needed to not have any prompt during package upgrade and installation, because we want to build the Docker container in an unattended way. The lines 18 and 20 do an update and upgrade of the minimal Debian distribution. On line 22, the backslash at the end of the line means that the line continues on the following line, so we have a single command from line 22 to line 50 to install additional packages needed by Buildroot. Line 52 is to set the locale to US standard, because sometimes my Ubuntu Linux try to set up something in Italian and this usually creates problems. Line 56 creates an additional folder inside the Docker container where we will put some additional files. Line 57 copies the startup.sh script file from our host Linux PC inside the Docker container in the folder created in the previous step. Line 58 makes the startup.sh script executable. Line 59 defines the entry point commands, the commands that will be executed when this Docker container will be powered on. This is different from a virtual machine, because when a virtual machine is powered on, the bootloader and the kernel start first, then the kernel will start the init process, and then the init process will start the startup scripts. In this case, instead, we don't have any bootloader, we don't have any kernel or any startup scripts. We have only the processes started by the entry point command that will run as if they were running on a Debian Wheezy Linux machine. This container is built using the script docker-build.sh that executes the docker build command that takes as a parameter the name of the container and as an argument the current directory where the Docker file is located. This command will build the container according to the instructions in the Docker file. It will download from the Docker registry the Debian minimal distribution and then will build the container parsing each line in the Docker file. When the building is terminated, we can run this container with the shell script dockrun.sh. This script defines some environment variables that will be passed to the following dockrun commands. These variables are to define the current X-Windows display, the current username, user id, primary users group, primary users group ID, the user's home directory, the user's shell, and the current working directory. Then we execute the dockrun command to start the Docker container. The parameters are -h to set the host name of our Docker container, -rm, this is very important. This clean up the container and removes any file system modification done by the container when it exits. If we don't use the -rm option, there is the risk that each new invocation will create a new Docker container without removing the old exited one. -v to mount the temporary x11 folder in our host machine to the same position inside the Docker container. This is needed together with the display environment variable to run graphical programs in our Docker container using the display of our Linux machine without any additional software. A second -v to mount the home directory of the current user to the same position inside the Docker container. This is needed to transparently share the entire user's home directory between the host machine and the Docker container. Many -e options to set the environment variables inside the Docker container to the same values defined above. The username, userid, etc. will be used to create a user inside the Docker container with the same username, userid, and group membership as the actual user to transparently share the user's home directory without access rights problems. The -it option specifies to run the container in interactive mode and to allocate a pseudo TTY to interact with it. The argument specifies the name of the container to run, the Giampietro/buildroot-mips 4kc in this case. We have seen above in the Docker file that we have defined as entry point the script startup.sh that has been copied inside the Docker container. The Docker container is its own /h folder, and so it doesn't have the same users as we have in our host Linux system. To easily share the home directory without access rights problem, we create inside the Docker container a new user with the same username, userid, and primary group membership as the current user in our Linux machine. We assign the password Docker to this user inside the Docker container, but this password will never be used. In our case, the grunx term is always 0, so we execute a su to the just created user, and before exiting, we start another root shell to do, if needed, some activities as a root before terminating the Docker container. We are now ready to proceed with the Docker installation and the creation of our Docker container based on Debian Wheezy, which was released in 2013, and that has more or less the same age as the software on our sample router. We will use a light Ubuntu version 19.10. We start installing Docker with the sudo apt-get install docker.io command. It will take some time to download and install the package. We check that the related services are running, but we can see that the Docker service is disabled. We enable the Docker service, we start it, then we check that it is enabled and that it is running. If we try to run Docker running the demo Hello World Docker container, we receive an access denied error, because normal users can run Docker only if they belong to the Docker group. By the way, if we try to run some image with the docker run command, if Docker will not find this image in our local machine, it will search the image on the official Docker Hub registry, link in the description below. In this case, the Hello World image is available on the Docker Hub. So we add the current user to the Docker group, check that it has been added using the groups command. But if we use the id command, we can see that the current process doesn't belong to the Docker group. This is normal in Linux because each process initializes group membership only at startup. This means that if we execute the docker run command again, we will receive the same error. The simplest and cleanest thing to solve this issue is to do a logout and a login to start with the new process that will read the new group membership. In this case, I am connected using an SSH session because I have the screen recording software installed on my MacBook, and because my MacBook is a much higher screen resolution that gives a higher quality screen recording. Now, the id command shows that we belong to the Docker group. Now the docker run -it hello world will run successfully, pulling the image from the Docker Hub registry and then running it. We can now build our Docker container, specified in the Docker file with the docker build command that is in the docbuild.sh script. This command can take a few minutes to complete. We can see that this command will load the minimal Debian Wheezy Docker container from the Docker Hub registry, then it will execute each line in the Docker file and continue to build our container, including the line to download and install a lot of additional packages. Once built, our container image is ready. We can have a list of available container images on our machine with the command docker images. If we use the option -a, that means all, we can see all the intermediate images that have been created for each line in the Docker file. These images use a layered file system, so each image contains only the differences between previous layers. And if we change something in the Docker file and rebuild the image, the layers are rebuilt only from the changed line onward. This is a very efficient way of managing Docker containers. We can have a list of running Docker containers with the command docker ps. If we want to include the list of containers that are exited, we can include the option -a. An important thing to understand is that if we run docker run multiple times, we end with multiple containers in an exited state that will consume some disk space and that usually we don't want. We can get rid of them with the docker rm command. We can prevent this from happening using the --rm command line option in the docker run command. We can see that now we don't have any more containers in an exited state. We are now ready to run our just created Docker container. We split the terminal in two. On the above terminal we are in our Linux host machine. On the below terminal we launch our script dockerrun.sh that uses docker run to run our container. If we execute hostname, we can see that the hostname is different in the two terminals. Above we see the name of our Linux machine, ubvm in our case, and below br host, that stands for Buildroot host. If we execute uname -a, we can see that the output of this command is almost identical. This is because we are running on the same kernel. If we execute a cat HOS release, we can see that above we are in Ubuntu 19.10, below we are on Debian Wheezy. If we execute a pwd command and the ls command, we can see that above and below we are exactly in the same home directory. If we execute a wmi and id command, we can see that we are exactly the same user thanks to the startup.sh script. Only group membership is slightly different, but this is okay for our purpose. If we execute the command ps-ef to have a list of all the running processes, we can see that above we have a lot of processes. Below we have only the processes started by the startup.sh script. That was the entry point script on our Docker file. In the above terminal, if we search the process startup.sh, we can see that we have the same startup.sh process, but with a different process ID. In the above terminal, if we list the process tree starting at the same startup.sh process, we can see that we have exactly the same processes as in the terminal below. This means that the processes in the Docker container are normal processes in our Linux machine. We have no overhead in running the Docker container. Inside the Docker container, we see only the processes started by the startup.sh script and with a different process ID because of the Linux isolated namespace feature used by Docker. If we use the free command to see the available RAM, we can see that above and below we have similar results. The two commands give slightly different outputs, but the information is almost the same. This means that the Docker container has zero overhead and that its processes will use the resources they need only when they need it. In Docker, it is possible to limit the maximum amount of resources available in a Docker container, but we don't need this feature for our purpose. If we check the GNU C compiler version on BAT terminals, we can see that on the Docker container we have available a much older ZCC version. The old Buildroot will love much more this version than the newer one available above. If we check the GNU libc version on BAT terminals, we again can see that we have different versions, and again the old Buildroot will love much more the older glibc version. We are now ready to run an old version of Buildroot in our Docker container to build the kernel and the root file system for our QEMU-based emulation environment. We will do this on the next episode of this series. If you have found this video interesting, please subscribe, help this channel grow, share this video with friends interested in hardware hacking. Please click the subscribe button and the notification bell to be notified when new episodes will be released, and don't forget to click the thumbs up icon. Please give me feedback and don't hesitate to ask me questions writing comments below. Let me know if you have suggestions to improve this channel or if you have enjoyed or not this video. Every comment, but positive and negative, is welcome. Thank you for watching. See you again on this channel.